skewed distributions? So today we're going to have a distribution that looks like this. I actually call it the Jabba the Hutt distribution. And just like the normal curve, by the way, let's do this. Here's the normal distribution. One representation of it. It could be fat, it could be skinny, but it's basically got to look like a bell, so forth. Can somebody give me one formula that related to this picture that we could find things on it using a certain formula? We've had several of these.
What are you looking for?
Huh?
What are you looking for?
What formula do we use to locate things in this picture? Say again? Okay, so they're related. I agree with you. But what is a confidence interval built on? That, huh? Z-scores. So what's one formula for a z-score? Any formula, I'd say.
The u minus x minus u over r.
Standard deviation?
Yeah, that's it.
Fat R, I'll take it. All right, that's one formula that relates to that picture. I calculate it, I get some z-score, I know where the data point falls in this picture, right? We've done that so many times. Can somebody else give me another formula? Anybody, just some with P's and Q's in it, right? Isn't there? Well, like you know it, Chad. All right. So P hat minus P over the square root of P, Q over N, right? That thing. That takes percentages, but it's still, it takes a percentage and it converts it to a z-score and it finds it on that picture. Now, of course, both of these require, like this requires n greater than 30. This requires np and nq greater than or equal to 5 to know that it's a normal distribution. Are you guys semi with me? So I have this picture, it exists. It just exists. So how do I find data in this picture? Well, I use these formulas and I know kind of like where they fall in this picture. Or maybe. So this picture is really just z-scores and how they kind of like fall and what percentage falls between them, blah, blah, blah. Okay. How far does this side go? We really didn't talk too much about that, but how far does that side go? What do you think? Infinitely long. So it goes to negative infinity, and that one goes to infinity. Right? Now, so this one tells me, for example, how means are distributed. And it tells me how, so sample means, sample percentages. Okay, I love it. What governs how skinny or fat the distribution will be? What number tells me how skinny or fat it's going to be? Standard deviation. So sigma controls the shape of this. Not the bell shape, but the general how stretched out or how compressed does it look. How we go so far? Now, all this stuff is old news, but I've never said it the way I'm saying it right now because there wasn't really a reason to before. Okay, so this is great for hypothesis tests. In that case, I would do this, right? This kind of formula is good for hypothesis tests about means, so I can see where the means fall and see if they fall far enough away from the claim, right? That old stuff. And this is really good for, obviously, hypothesis tests about percentages. Okay, maybe. So, and also I could use a modified version of this to help me create, like you said, confidence intervals for means, for percentages. All right, Jeff. So enough of that shit. So what if I wanted to do a test about a standard deviation? What if I had a claim, like my claim is, I think the standard deviation of samples is, I think it's going to be greater than 9 or something. What if I have a claim like that? Why does it not make sense to use this distribution then? What is this distribution built on? It's built on taking every possible sample and plotting the sample means, right? So every little dot is a sample mean. Because then I can compare one sample mean to all of them and just see where it falls relative, okay? If I want to do a test about frequent standard deviations, then this picture has to be every possible standard deviation of every sample. So what makes this picture are a bunch of freaking S's. I calculate a S, I'll take a sample, calculate the standard deviation, plot it. Take your sample, plot it, okay. So I really want this to make sense. I can't use a normal distribution for that because that's not how standard deviations themselves are going to be distributed. Can somebody tell me, what is the absolute smallest a standard deviation can be? 0. Right? That would mean every data point is the same. 3, 3, 3, 3, 3, 3, 3. Okay, that's got a standard deviation of 0. They get 0 away from their mean. The minute one of them is anything other than 3, standard deviation becomes positive. You guys can. So if this picture is supposed to capture these, then that's got to be 0, and that's a hard wall. You can't go past that shit. So then it goes forever out that way. This way goes forever. Yeah. Okay. Maybe. I really want you to understand why all of a sudden we're abandoning this thing we've used so much and we're using something else. Because this tells me how the shape of all of these and all of these will look like. So if I want to do a study on him himself, what the shit does he do? He does this thing. Partially because it's got this hard wall, so it's going to be slammed up against that wall. Maybe. Okay, this is all weird shit. I know. So, let me show you an example of this kind of formula that could be used to find something in this picture. Are you with me on that? Like I make a z-score. If I get a -1, I know where that thing falls, right? I want, what formula goes with this weird shit so I can tell where something falls? Well, here it is. You ready? Here's the formula. What is this? Which is the degrees of freedom times S squared. What's S again?
The standard deviation of the sample.
Standard deviation of sample divided by sigma squared. So if I take a sample and I square sample standard deviation, I get multiplied by the degrees of freedom divided by the standard deviation of the population, I'll get something that's like a z-score. I want you to really see how in a z-score I take my sample data and I compare it to my population data. Yes? Yeah. I do it through subtraction in that case. In this case, we're doing it through division. I take a sample and I compare it to the population. What if the sample happens to have the same standard deviation as the population? What would happen? If these two are the same, they would just cancel. You know, so the highest peak actually correlates to the degrees of freedom because that's sort of like what's going to happen most. It's going to be around that. Okay, maybe. Okay, this is all really weird. I understand. By the way, this is a small point, but if I take a normal distribution and I fold it on itself, I get this kind of shape. And actually, it only works for, I don't want to get too deep into this, but it's kind of, I'm going to show one thing when I give you this chart just to make the connection. Let me give you the chart. So this is just like the T and Z score chart. So for one crazy thing. So let's see.
God damn it. I knew you were going to give me chi-squared test.
This, by the way, is our last chart, our last new chart. So if you love them, I'm sorry. If you hate them, I'm sorry. All right, let's take a look at this thing. Anything on there look at all familiar?
Not at all. I'm so lost.
Degrees of freedom.
There we go. Yay. So the one thing I haven't put up here yet, let me see if there's any policy. You're gonna love this, you ready? You're just gonna love this.
Is it a Greek symbol?
It's the Greek letter chi. It's like, of course, an x. Chi squared. You can't take a square root of this. That square is a part of the symbol. So it's the chi square. And it kind of relates to what I said about folding a normal distribution on itself. You square all the values.
Okay.
So do me a favor. Well, let's look at this thing real quick, and then I want to try to point out a couple things. And by the way, right now, don't even try to guess what your work is going to be. Just realize it's not going to be as bad as you're imagining, okay?
I feel like it is, though.
I know that. I don't blame you at all.
I know what you're saying, and what you're saying makes sense. But
Okay, that's
feel
my favorite
very
phrase.
stupid.
Don't. This is brand new shit. This is weird. This is weird. I'll be the first to admit that. So let me do one thing to connect this with something we've done. Notice one really crazy. You guys have all your Z-square charts? If you don't, it's okay. Do I have one for me? Probably not. It's okay. Can anybody remember for a 95% confidence interval, what were the Z-scores? 1.96. Now, real quick, if I fold this on itself, which is weird, I understand. So basically what I'm going to do is I'm going to cut it right here. I'm going to fold it. So I'm going to add these two. Can anyone tell me what area is in this tail?
That part right there is plain. It is what? 2.5%.
Yes. And of course over here the same thing. So if I fold this over, I'm going to end up with 0.025. I'm going to end up with 5%. I'm going to fold it, right? Which means, so it's going to end up with, to be honest, it's going to end up looking like this, but that's all right, because for degrees of freedom of 2, it gets all, I'm sorry, 1, it gets all freaky. Just stay with me for a second. So now I'm going to have 5% to the right of the critical value. What is it for degree of freedom of 1? 3.841. Can you guys, real quick, get a calculator? What is 1.96 squared? Is going to fold this and they're going to multiply.
3.841.
Yes. And the reason it's not, it kind of like comes out a little bigger than that is because 1.96 is a little bigger than the actual value. It's rounded, right? Yes. You good?
I have a question.
Yes.
That might be foolish.
Sure.
Why are we squaring instead of doubling it if you're
Folding it on.
Because the reason this is a chi-square, there's a lot behind this, is because you are looking at the distribution of squared parameters. So there's a lot more behind this that we don't have the time to get into, but I at least want to show you. Do the square root of 2.706.
Okay.
Or do, well, yeah, let's do it this way. Do the square root of 2.706, please.
1.644.
So 1.6449, right?
Yeah.
1.645, does that sound familiar, 1.645?
Yeah.
That's another z-score we've used in the past.
Yes.
So basically everything up here are old z-scores we've used in the past squared. So there is a larger concept that this one thing fits in that we don't have time to get in. Oh shit. The reason we do this in Stats 1 is we want to just lay the groundwork for the existence of this distribution. We want you to know it exists, and then depending on where you go, you might do more with it or not. And I know some of you guys are like, this is the last damn thing I'm doing. All right, I understand. Okay, now let's get into the nuts and bolts. All that is concept. All that's concept. None of what I just said is anything you're going to have to do yourself. ever, right? Let's talk about how are we going to actually use this now that we sort of understand a little bit about where the crazy ass distribution comes from. All right. Do you see how there's multiple formulas that all relate to the same shape, right? We've seen that with normal distributions already. Chi-square, the same idea. This is the real basic chi-square formula. It's sort of like this guy that we talked about way back in chapter 2. That's the basic foundational thing, right? So what I do to construct this picture is I take a sample, find a standard deviation, I can just say variance, divided by the population variance, times the degrees of freedom, and I plot that point. And I just keep going. So the absolute smallest this could be is if my standard deviation was 0. That's why that's the lowest it can go. It can't go negative, right? You guys with me? Yes?
If your standard deviation was 0, wouldn't that be like unsolvable? Is that
Not the
basic?
population standard deviation.
Okay.
If the population standard deviation is 0, why? There's very little purpose to do any analyzing. Everybody's the same. Why would I do any statistics? Because everybody's the same.
I have a question.
Yes.
So, population standard deviations on the bottom, but the sample standard deviations on the top?
Yes.
Okay.
I love it. Okay. So, just like with normal distributions, there's multiple formulas to calculate the same z-score that relates to this thing. So I can find, even if it's a mean, I can find it. If it's a percentage, I can find it. There's multiple formulas that relate to this same shape. So let's get into what we're actually going to use this for. And what it's called is a goodness of fit test. It isn't my name, it's just a name it's been given. So for example, let's say that, I think the example I gave there was, oh, cool. All right, we'll just do this one. Oh, okay. Let's say I've got a bag of M&Ms. And I'm curious about if the colors in the M&Ms are uniformly distributed. So I think there's brown, yellow. I can't remember if they've added any new ones. There's red, blue, orange, green. Is there any more than that?
Probably not.
Okay, take on. Okay. So those are my categories. How many categories are there up here? 6. Okay. It's going to be very important in a minute. So let's say I want to test to see if the colors of M&Ms are uniformly distributed in the bags of M&Ms, right? So let's say I take enough bags to get 42 M&Ms. Let's put observed here and expected here. I really want this to make sense. If I have a claim about something, that means I go in expecting something to happen. And then I observe something. And fundamentally in statistics, what we do is we see how far away is what we observed from what we expected. Yes? So when I take a sample, what do I expect the average of the sample to be? I expect it to be close to the real mean. And then I observe an actual mean from the sample, and I kind of take the difference as part of the z-score formula is to see how far apart those are, right? You guys semi? You're like, no, but keep going. Okay. So tell me, can anyone tell me, if I had 42 M&Ms, and my expectation is they're uniform, they're uniformly distributed, what does that mean again?
Or it means that they're all the same.
They're all the same. How many of each color would I expect then?
7.
7. There's 42 M&Ms, 6 categories. I expect 7 each. Okay, I like it. And there's only 2 things I could give you. I could either say they're uniform, in which case you just take the total divided by how many categories to see how much each one gets. Let that make complete physical sense. There's another way I could give you it, and we'll do an example like that here in a bit. Now, for this one, on a problem, I'm going to have to give you these. In the real world, you would just open the frickin' bag, and you would count how many brown, how many yellow. So let's say that I've got, I've opened the bag, and I got 5 brown, 6 yellow, 5 red, 10 blue, 9 orange, and 7 green. And hopefully that adds up to 42.
Yes.
Thank you, guys. So that's the answer to everything, so that works. Now, just on the surface, just looking at this, did that bag meet expectations?
No, and you should swoop.
Yeah, damn it. I don't know if the M&M company has an actual thing saying, these are uniformly distributed. If not, then we cancel. Remember hypothesis tests. If I had a claim I thought the mean was bigger than 9 and I get 9.2, can I just stop? Can I just go, there you go? That's freaking evidence. It's bigger than 9, isn't it? Because it was just a sample we took, yes? And samples, I expect variability. So on the surface, these are very different. Not very different. I didn't get like all blue. That would be neat. Right? They are different though. So please understand, we're not going to do a full hypothesis test here, but it's the same foundational idea. How different was what I saw from what I expected? So what do you think the very first thing to do here that makes sense? If what I'm curious about is how different are these two? Take the differences, right? So what is observed minus expected in each case? -2, right? I mean, doesn't this make sense? If I'm curious about how different was what I saw from what I thought I would see, mathematically, take the difference. That makes immediate sense. Yeah. Okay, only green did what I thought it would do. Now, do you remember when we were developing standard deviation and we got negatives? What did we have to do? The same thing we have to do here. We have to square. I like it. So we have 4, 1, 4, 9, 4, 0. For the same reasoning, I've got to square these. Now, let me ask you. If 2 numbers were 2 apart, is that a big difference?
Depends on how big the number is.
Thank you. That's the correct answer, right? You don't know how big 2 is. We're in statistics. You guys should all know by now. If I say, is 81 very far from 80? You should say, I don't know, Jeff. What's the freaking average distance of things, right? Does that make sense? I don't know if 81's far from 80. Before this class, you would have said, yeah, 81's freaking close to 80. What are you talking about? But the standard deviation's 0.1. 81's 10 steps away. So, the next thing here that makes sense is to get an idea of the relative difference between the two. So if my expected value is 7, then a squared difference of 4 is kind of big. But if my expected difference is 7 billion, I mean expected amount is 7 billion, and I'm 4 off squared, that's pretty damn close, right? So it's relative to the actual size of what I'm dealing with. So I just divide by E. So somebody help me out. I think that's 0.5714. 4 divided by, so I'm doing 4 divided by 7, right? Each one of these divided by the expected. 5714. This is 0.14 something.
1.
28?
Yeah.
So I'm not sure how I feel about this, but I have my divided by 7 sort of memorized. It's good. More in your mind.
I think of everyone to have done it, I think a math teacher is the least weird.
Least weird, true. But I'm not sure how you guys would feel about it. So this will be 1.2856.
5.7. Come on.
Ooh, I suck. And then this will be again, so I got a bunch of 4s. And this one, oh man. So, the fundamental chi-square that kind of builds the picture, of course it's facing this way. We missed all of that stuff. Everybody who didn't come. Well, be glad I'm videotaping. I actually thought about maybe not videotaping, so just be happy. Okay. The fundamental thing that builds the picture was this guy. This is the formula we're not going to use right away. So this is kind of like the fundamental one. The one that relates to this guy is exactly what we just did, except it's the sum of those. So this is relatively simple to make. It just is. It's just relatively simple to make. And then I just have to add these up. So help me out. Can anybody add these up relatively quickly?
Okay. 3.1427.
Okay. This is a measure of the distance. It's sort of like a z-score, but not completely. So it kind of measures how far apart things are. Okay, now, this is the nuts and bolts calculation. This is kind of like doing z-star. All of this right here is kind of like doing z-star. It's kind of like our data. What does it give me? So let's go and see what in a hypothesis test, don't I have to relate that to where the rejection region is? Yes? So listen, when I do this test, what would it mean if I got 0? What would it mean if chi-square, if this added to be 0? What would that mean? What would have to happen? That's the only way these could add up to be 0.
The observed match the expected.
These would have to be perfectly matched, correct? If these are all 7s, is that evidence against them being uniformly distributed? If I get all 7s,
That's evidence for them.
that's actually evidence for. It's not proof, it's nowhere near proof, but it's definitely not evidence that they're not uniformly distributed. So I really want 0 means what you saw perfectly matched what you expected. With me? So just like in a hypothesis test, not only do we have to be different, we have to be different enough. I have to figure out what is that benchmark that I got to get past? What is that rejection region? So it's going to be up here, kind of makes sense. Not only do I have to be different, I've got to get past a certain benchmark. So if I ask you for the degrees of freedom, you're going to give me the wrong answer, but I don't mind. You would think that the degrees of freedom would be 41, correct? And I wouldn't blame you.
6.
Almost.
5.
There it is. So the degrees of freedom for a goodness of fit test is the number of categories, which for some reason, I love this. They use a K, because they can't spell, minus 1. So it's still the number of something minus 1. But it isn't the number in my sample, it's the number of categories. Yes?
Then what is C?
Huh?
Is that because C already stands for something in stats?
No.
Or is it just?
To be honest, K has other meanings, so it was sort of, it's just funny. It's just kind of coincidence. K was already used, so they just used it here. But I always loved to see, I just can't spell categories, but the real story is K was used in other things, and they just sort of ported it over here too.
The reason it's like they use a misspelling is because of, or it's just German.
That's a good point.
That's also the answer.
But it's just a differentiate. It's definitely not n. So you can't use n. Naive. So, degrees of freedom for this is 5. What if I want to test this using alpha equal to 0.05? Can you look up there? So that means that the area in the tail is 0.05, correct? So can you find the correct chi-square score that would tell me what the rejection region is? What far enough away is? So I got 0.05 into the right of the thing, right? So to the right, 0.05. My degrees of freedom is 5. So 11.071. So in order to show evidence, in this case, that they're not uniformly distributed, because 0 would mean my sample was perfectly uniform. Going past 11 means, holy shit, you're pretty far away from being uniform, right? But where did we make it? Where did we make it? Where did we get? We got here. We got like 3.1425. So can we reject the claim that they're uniform? Did we make it far enough away?
Absolutely not.
Nope. Fail to reject that it's uniform. Let me see, what was this one like? Oh good, this is perfect. Yeah, okay. So what I want you to do on the little group worksheet, see number 3. I want you to try number 3. Try to get the table figured out, because that's just computations. That's pretty straightforward. And then I'll show you. You can use your lists in the calculator to do it too. So we'll go over that here in a minute. By the way, I'll go ahead and give you this. This is basically just the problem we did. We'll do this sheet in a minute, but focus on number 3 on that group worksheet. But here's the example we just did, sort of written in a way you can read, so the computer did it. So you found, oh yeah, it's the same one, yeah, exactly. That sounds familiar. Yeah, it's pretty straightforward. Divided by D, right? Divided on by 20, looks like it, yeah, looks good. But it would be a little more explicit and fail to do what?
Fail to
By the way, just to make sure everybody's understanding number 3, I don't say this, but if the die has not been tampered with and I roll it 120 times, how many 1s do I expect to get? How many 2s do I expect? Should I expect to get any of them more than the other ones? Which means it would be a uniform distribution. I should get the same amount of each. Now real quick, be careful how I say this. If you roll a die 120 times, would you put money on getting the exact same number of 1s, 2s? Hell no. But don't we expect? Isn't that the best thing to expect? Yeah. Okay. So that's how you fill out your expected. It's exactly like we did with the M&Ms. So just make sure everybody's off to the right start. How many ones do you expect?
20?
Say again.
Only 20?
How'd you get that?
120 divided by 6?
Okay. So you take the total number,
Oh.
divided by how many categories it could fall into. Right? Each category is supposed to get the same number. So it's got to be just the total number of times you did something divided by how many categories. I love it. So it's just 20 all the way down. It's 20s all the way down. And then I just have to tell you what the observation is, because I'm not giving you all dice. That would be horrible on the day of the test, just a bunch of people rolling dice. So I just tell you what happened. So if you wanted to do this in the calculator, I could make this one. Why did I put expected first? Sorry. I can make this one L1, this is L2, L2 minus L1 squared. Then you can figure out what that one would be, so try to finish that out. So I really dislike is, thankfully none of you guys have said this to me, but you start to talk with other people taking other stats courses, and they say, oh, this other teacher doesn't make the students do any of this. I'm like, well, that's because they suck. I want you to always be connected to the main idea of what gives you the number at the end. And you can see it's based on how far apart these were, and then the relative distance. I mean, if you just punch buttons, you're not going to have any connection to the number that comes out. So, anyway. So can somebody tell me? Even if you didn't do it in the calculator, could anybody tell me what this would be? So this is L3. What would you put here?
Do L3 divided by 20.
Yeah, L3 in this case divided by 20, but in general you could do it divided by wherever your expected is. So go to L4, make it L3 divided by L1. Because there will be problems where these are not all the same. Yeah. All these numbers. No, O2 job. I'm not looking up there. Because then you can see it. If that makes sense. I understand. It sucks. Alright, and then if you want to, you can do the same thing we did before. We can do, get out of here, you can go to list, math, sum, Scheisse. I went the wrong thing. list, map, sum, arg, list, map, sum, there we go, L4. So it adds up to be 8.4. So kind of like the way I do these problems is sort of backwards, but that's fine. I go ahead and just attack the table, get that calculated. This is sort of like our Z star. This is our sample data. That's pretty far away. The one we did up here was 3 away. So now we're 8 away. Now, of course, this problem was 6 categories. Alpha was 0.05. So to be different, I made this one 6 categories. Alpha's 0.05. So what would the chi-square for the rejection region be? 11.7. Same one, yeah. So if I drew this picture, it'll be 11.071, I think it was, and then we got 8.4. We got closer, but we didn't quite get in there. What would 0 mean again in this case? Very specifically, what would 0 mean?
That you rolled exactly what you expected.
Yeah, that we rolled exactly all 20s. So if I get here, that is evidence that the die was tampered with. You guys with me? Does that make sense? If I get way the hell out here, I'm so far away from what would be expected if it was a normal die, that's evidence it's not a normal die. Something happened. Yeah.
So with your 0.05, what's it called? Your 0.05
Level of significance.
Yeah. Does that mean that if it exceeded that amount, that would mean that there's only a 5% chance that it was not tampered with?
Yes, roughly.
So
Yeah.
what does 0 mean again? Sorry.
0 would mean the only way to get a 0 at the end is if all of your observed was exactly the same as all these. Which is not proof that it's not been tampered with. It's just not evidence that it has been tampered with. Sort of the difference between saying innocent or not guilty. We always say not guilty because there is a difference
not
between that and
found.
innocent. Yes, yes. We have not found you guilty yet. Okay. Maybe. So this one is nowhere near as long as the hypothesis test. All I need you to say right here is we have not found evidence that this has been tampered with.
Is it acceptable to write failed to reject, or was failed to reject hypothesis?
Well, in this case, it would be failed to support the claim, but enough to get that specific, yeah. Because the claim is it's been tampered with, so we failed to support that claim. Yeah. Okay, maybe compared to some stuff we've done in this class. That's kind of nice. Even the chart isn't that crazy, that it's a whole new kind of thing. Okay. So let's look at this other one I gave you. Go ahead and try this one. So here's the one we did earlier. I've got it all nice, all written up, look even all colorful and stuff. So I want you to try this one. This is the first one we're having that is not uniform. They give us percentages expected in each category. So I've kind of helped out a ton. So try to do that problem. Just to give you a hint, I think this one is one where we finally succeed. So let's see what we get. Oh, that's right, it's back there. Oh, yeah, that's right. Okay. Yeah. Just make sure everybody's on the right track. Observe. Pretty much have to tell you. And the rest, oh shit. So in the case where I give you percentages that are supposed to fall in the categories, I've pretty much put here what you're supposed to do, but it should hopefully make sense. I expect 20% to be below 130. So of course I expect 20% of the number I look at to be below 130. So in the case where I give you percentages, that's all you do to construct what the expected stuff is. Does that make sense? No?
So it's like 0.20 or.
Yeah, good. So in the
0.5.
calculator, it's just 0.2 times 500.
Okay, yes, so it's
Yeah.
100.
So it's 100, yeah. 150.
175.
75.
75.
70. By the way, I didn't say this, but this is the bad cholesterol. So what's the better thing, of course, is to have lower amounts of it.
Yeah.
So does it look like, just on the surface, this is not good enough to say any evidence for anything, but does it look like they do better than the general population?
So
Do they have, yeah, there's less than 130, 130 to 200, 200. So they had
Yeah.
more people with less cholesterol and less people with more. So it looks like, for some reason,
Pretty good.
we do. Okay. But now I got to see if it's good enough. So in the calculator, you could put this is L1, this is L2. I normally put observed first just because, but I want to do that one in a different way. So in L1, I would put the observed. L2 goes the expected stuff. And here, if you wanted to, you can even just build the formula right in. You get 0.2 times 500, bam, right? So you can just do it all in this table itself. And now I want to let L3 be, in this case, L1 minus L2. It doesn't really matter since I'm squaring, but L1 minus L2 squared. Crazy sauce. Those are huge, but then I have to do this divided by E. So in the calculator, it's going to be, like you said earlier, L3. In this case, it's going to be divided by L2, because that's where the expected is. So if you don't want to, you don't have to do it in the calculator. Not a dang problem with that. But I get these numbers.
tall. So it'll be like 324 divided by 100.
Say again.
So for like.
Yeah, it would be
Okay.
324 divided by 100, and then 2304 divided by 150.
Okay, I was just making sure.
So you have to, for each row, you have to do whatever that expected is.
Alright.
So then I can add this up and get what my chi-squared is. And again, chi-squared is just a measurement of the relative difference between observed and expected. That makes so much freaking sense. I'm just seeing, am I seeing something so different from what I expected that it's evidence that the whole population is different? So that should come out to be pretty decently large. It's like 35 or something. 35 point, maybe it's 36, I don't know. Yeah, 36 points, I think.
36.1163.
Crazy. So something else, that's our, like our Z-star. What's alpha in this problem? Now we got to figure out a rejection region to see if we made it far enough away. What's alpha? 0.01. Somebody else tell me what's the degrees of freedom?
3.
Beautiful. Right, 4 categories. Degrees of freedom is number of categories minus 1. So don't say anything if you haven't done it yet. Look up the chi-square for that in the chart. So the 0.01 degrees of freedom is 3. All right, what do you guys get?
11
Yeah, 11.345?
Yeah.
So where's 36?
A lot past that.
Look at this shit out there. Now, in general, you would just say that this group does not fit the general pattern, but in this case, we can be more specific.
This group has lower.
Yeah, this group has lower cholesterol. So there was a huge craze back in like the 70s, 80s or something. It was the Mediterranean diet, because it was noticed that people that lived in the Mediterranean were generally healthier. So as Americans, what did we do? We went and said, olive oil.
Fish.
Everybody, use a ton of olive oil. That'll make you lose weight. It's like, what the shit? What are you talking about? So we just sort of like found the most general, everybody seems to use olive oil. That must be the answer. When of course it was, they have walkable cities and they eat healthier, fresher foods. But we kind of went like, everybody's just dumping olive oil and everything, thinking, I'm losing weight. So these kind of statistical analyses are initial. This is the first thing you would do. And then you would go in with experiments. You would have variables that you would control. You would see, well, this village doesn't eat as fresh as this one, so is it the fresh food? Is it the whatever? You would try to do experiments. You try to see what's the differences, right? This does not do all that. This just says, they seem to look this way. We don't know why. It just looks like that's what's happening. Are you guys, is that all right? Yeah.
For this case, wouldn't it be proof instead of evidence? It would be proof that this group has lower cholesterol than ours rather than evidence towards it.
Yeah, in this case, the way I worded it, I had the whole population. I should have said, we take a sample of them. Because otherwise, you're right. If it's the whole population, then that they definitely do have different cholesterol levels, right? We still wouldn't know why, but yeah. But that's more my just not putting the right words down. Okay. So I think what I'm gonna do, let me see. So on Tuesday we've got the chapter 12 quiz. Tuesday. I'm gonna have the practice final exam that I'll give you guys On Thursday will be review day. I think we might actually start reviewing even on Tuesday after the exam is done. I don't think I'm going to, there's just too much to get into to be even able to do the rest of chapter 11. Does anyone got their homework sheet right there accessible?
The homework for chapter 11 goes up to 11.
What's the sections?
11.1, 11.2, 11.6.
Yes, let's just put it on 11.6. Okay. That's what I was thinking. I couldn't remember if I had put in the intermediate sections. 11.6, I think you're happy for that no matter what. But 11.6 is where we use this when we're doing hypothesis testing for standard deviations.
Yeah.
Exciting, right? So there's just nowhere near enough time to get into that much depth. Okay, so hopefully this didn't freak anybody out. It's pretty straightforward. I know the chart's brand new, and I need you to understand this. This is not even scratching the surface of what the chi-square is used for. If any of you go into any fields where you do any stats, you look at anything, there's so many other uses of chi-square, but we just want people to be aware of it when they come out of stats 1, elementary stats. Okay, yeah, so that's plenty. Yeah. So Tuesday we'll have the quiz. Final is coming fast, right? Next week is the last week of classes, so I am going to update my finals week schedule, so I'll give you that. Because of course my finals will be 2 hours long, so it's going to disrupt my schedule and blah, blah, blah. So I'll let you know exactly when I'm in the Math Study Center, when I'm going to be in here before the final, all that kind of stuff. Okay, but next week is going to be normal in terms of classes and such. Okay, thanks guys. If you borrowed a calculator, don't forget.
On the feet.
Thanks. Oh yeah.
I got a question.
Yeah.
Jonas, you get a 50 on the 240.
Oh, real quick, because it said the rest. So I just saw that these added up to be 447. There's 500 people, so the rest of them 53.
Oh, okay.
Yeah.
Okay, thank you.
Yeah.
For next week's quiz, we just have to like memorize how to do the stuff in the calculator.
Oh, for the linear correlate? Yes.
Okay.
Yeah. And then part of the quiz is going to be coming up to show me the dots and the line of best fit.
Alright. Thank you.
Sure.
I know I have a test or two to make up.